In this lesson, we're going to learn about intermolecular forces. So there are two main categories of forces: intramolecular, which are bonds within a molecule, and intermolecular, which is forces between neighboring molecules. So intramolecular forces we talked about are similar to intramural sports, which is competition that happens within a school. And so intramolecular forces or bonds are the forces that are within a molecule. So if I have a molecule of water, the bonds between the oxygen and hydrogen atoms that are within one molecule of water are the intramolecular forces or intramolecular bonds. So quick review. And this is a good place for you to pause the video and try these on your own. So between each of these types of atoms, would there be polar, nonpolar, or ionic bonds? So once again, I recommend that you pause here and see if you can determine which types of bonds these are. So carbon has an electronegativity of 2.6 and hydrogen has an electronegativity of 2.2. So that is a difference between the two of 0.4. And hydrogen, once again, 2.2. Nitrogen is 3. So the difference between those is 0.8. Magnesium is 1.3 and chlorine is 3.2. So the difference between those two values is 1.9. And calcium is 1 and fluorine is 4. So the difference between those electronegativities is 3. So to determine what type of bond we have, anywhere from 0 to 0.4, which would be this one here, is a non-polar bond. Anything between 0.5 and 1.6, which would be the 0.8, is a polar covalent bond. So these are both covalent bonds, non-polar and polar. So both of those involve a sharing of electrons, which makes them covalent. And anything 1.7 or greater is going to be ionic. So both that and that. So magnesium chloride and calcium fluoride are both going to be ionic bonds. So those are the intramolecular forces. Those are the forces between atoms within a molecule. So we talked then about whether something would be a polar or a non-polar molecule. So carbon and hydrogen. So we have one carbon that's going to be bonded to 4 different hydrogens. So each of these bonds is a difference, and we just calculated it on the page before. So 2.6 and 2.2. So each of these bonds has a delta En of 0.4. So because the bonds themselves are non-polar, the molecule can't be polar. So this is a non-polar molecule because all of the bonds are non-polar. Now with methane, because the molecule is symmetrical, even if the bonds were polar here, the molecule overall would be non-polar because the delta En of 0.4 in 4 completely equally spaced directions would end up canceling out. So one way or another, methane would be a non-polar molecule. For carbon dioxide, we have what we call a linear molecule. So it's 180 degrees from this oxygen to this oxygen, so completely straight across. And so we have between carbon and oxygen, so 2.6 and 3.4, so we have a 0.8 delta En. But we have the exact same amount, but in opposite directions. So here, although the bonds themselves are polar, so we do have a slightly positive and then slightly negative, But because of our symmetry here, because these vectors would cancel out, we have, once again, a non-polar molecule. So far we have non-polar bonds, which automatically results in non-polar molecule. Here we have polar bonds, but because the direction of those bonds is exactly opposite of one another, there's going to be a cancellation of the bond dipoles. So that there's no overall molecule dipole, which makes that a non-polar molecule. And then hydrogen and chlorine. So chlorine is 3.2, hydrogen is 2.2. So we have a delta En of 1. And here, because there is no symmetry, we're going to have chlorine is more electronegative. So that's going to be a slightly negative end, and hydrogen is going to be the slightly positive end. So as chlorine pulls hydrogen's electron closer to itself, so not an equal sharing, it's not strong enough to fully pull that electron over into its own valence electron shell, but it does pull it closer. So it creates this slightly negative area around chlorine and a slightly positive area around hydrogen. And so here, because we have a clear positive and negative end of this molecule, this is going to be a polar molecule. Okay, so we're going to need that understanding of polar molecules for intermolecular forces, which is what we're going to look into next. So intermolecular forces, so just like an interstate highway runs between different states, intermolecular forces are an attraction between different molecules. So we talked about the intramolecular bonds between the atoms in a molecule of oxygen. So now we're going to look at, if we have two molecules of water next to each other, what is the force that holds those together? And so we know at room temperature water is a liquid, so different molecules of water are near each other. And if we were to go below 0 degrees Celsius, they would turn into a solid. So there, they can't even move past one another. So there is some sort of force in a liquid and a solid holding molecules together. And those are the forces that we are going to look at today. So in ionic compounds, here we have the full gain or loss of electrons and then a full charge. So we have positively charged cations and negatively charged anions. And as we have those positive and negative ions created, the attraction between those is what holds those together. And in an ionic bond, because we have complete positive and negative charges, there's actually no distinction between what one molecule of an ionic compound is. So here I have sodium and chlorine, so that's sodium chloride. Before we would have looked at sodium has 1 valence electron, chlorine has 7 and needs 1 more. And so if we did our crisscross here, we have them in a 1-to-1 ratio. So when we talk about ionic compounds, the formulas, we actually often call them formula units, and it is based on the ratio of how many of each ion we need. So here, there's no distinction between this being 1 molecule of sodium chloride, or this being 1 molecule of sodium chloride, or this being 1 molecule of sodium chloride. And what that means is that the attraction between these two ions is the exact same strength as between these two ions and these two ions. So ionic compounds are crystalline solids, which means they form a very ordered structure where they alternate cations and anions. So we just saw that with the alternating positive and negatively charged ions. And the forces that hold a cation to every single anion, so on every single side of it, is completely equal, which is what I was just talking about. So you can't distinguish which cation and which anion are one molecule of an ionic compound. So here, there is no difference between the intermolecular and the intramolecular, which is why we can't distinguish which in this case, sodium and chlorine form one unit of sodium chloride. So as I have another unit of sodium chloride here beside it, and this continues, and these are all positively charged or negatively charged. So as we continue here, there is just a bond that is just as strong between every single one of these cations and anions. So we can't really distinguish what is one molecule of sodium chloride. And so this is where that idea of formula units comes in. We just look at the ratio of how many we need in sodium chloride. So I have just as many sodium ions as I do chlorine ions. So we have a 1-to-1 ratio there. So other intermolecular forces then, so ionic are intra and inter are just as strong. So that's the strongest force you can have holding anything together is an ionic bond. Then the next strongest is a polar covalent bond and then a non-polar covalent bond. And there's a range there as we go from a 1.6 delta En all the way down to a 0. So the bonds that hold atoms together within a molecule are the strongest. Ionic is the strongest within that, and ionic is the exact same for within and between molecules. So the next thing we're going to look at then is what are those forces between molecules when we have covalent compounds, and we have a very clear distinction between one molecule and the next. So the different forces we have are hydrogen bonds, which are very strong. Then we have dipole-dipole bonds, which are medium. Hydrogen bonds are actually a type of dipole-dipole, but they are stronger than other dipole-dipole bonds. And then we have London dispersion forces, which are very weak. And everything has London dispersion forces, but if it has a stronger type of force, then that is what becomes more important. That's the stronger thing holding two molecules together. So hydrogen bonds are bonds that occur between polar covalent molecules, but specifically when there is a hydrogen on one molecule that gets directly bonded to a fluorine, an oxygen, or a nitrogen from the molecule beside it. So here we have water. So water has hydrogen and also oxygen. So when we have, a hydrogen directly bonded to a fluorine, an oxygen, or a nitrogen. So in this case, we have hydrogen bonded to oxygen. So if we think back to our polar molecule, the bond between each hydrogen and oxygen was polar. And then because it wasn't symmetrical, those didn't cancel. So we ended up having the oxygen end of water was slightly negative and the hydrogen end is slightly positive. And that creation of those slightly positive and slightly negative, or partially positive and partially negative regions, will create an attraction to the opposite partial charge. So the partially negative charge on the oxygen is attracted to the partial positive charge on a hydrogen from a neighboring molecule of water. And so in between every oxygen and hydrogen from separate molecules, there is a force that is holding them together. So once again, the strongest force is within the molecule. So it's a lot harder to break the bonds in the molecule than between two molecules. But at room temperature, there is a force between neighboring molecules of water that hold them near each other. And if we cool down to below freezing, below 0 degrees Celsius, then that bond or force between these two molecules of water is now so strong that they can't even move past each other. So dipole-dipole bonds are the same as hydrogen bonds, except that they are not between a hydrogen and a fluorine, oxygen, or nitrogen. So we have the same idea though, where we have polar covalent molecules which have a partial positive and partial negative charge, and then we have an attraction between the partial positive side of a molecule and the partial negative of a neighboring molecule. So that is the same idea, only it's not as strong as the hydrogen bond. And then the weakest type of force which exists is called a London dispersion force, or also sometimes called van der Waals forces. And these occur between non-polar molecules. So here we may have had delta En, so I believe this one is 0.4. So we're getting close to being polar, but because of the completely equal distribution of those hydrogens, there would be a canceling out of the bond dipoles. However, with non-polar molecules, when we have a neighboring molecule coming close, what can happen is the force between those molecules, as something is coming close, electrons will repel from one another. So as one molecule comes in, its electrons can force electrons on another molecule to move a bit further away because those electrons are trying to repel one another. So as this is coming in and the electrons that are around here are repelling electrons on this part of the methane, they're going to shift a little bit, and that for a brief moment is going to create a dipole. So it's going to create this slightly positive and slightly negative section or area of each molecule, which will create then an attraction between them. But these don't last particularly long, and so the force between the molecules is not very strong. So they may for a moment have an attraction between them, but it doesn't last. And so this is what we have when we get to things like oxygen and nitrogen, which are gases at room temperature. So there's not a very strong force holding neighboring molecules together. So here, those black dashes between the molecules are representing those London dispersion forces. So a few examples here to look at. So hydrogen here, because we have two completely equal atoms, we're going to have a delta En, which is equal to 0, which is non-polar bond. It's also going to be a non-polar molecule, and non-polar molecules will only have London dispersion forces. So they are not, we don't have a permanent, partial, negative, and positive, which will attract them. So there we have London dispersion forces, which may create temporary dipoles, which would cause an attraction. Ammonia, so nitrogen is 3 and hydrogen is 2.2, so that has a delta En of 0.8. If we were to look at this in a 3D molecule, either using the PhET simulation or building it, nitrogen has a lone pair of electrons and then 3 hydrogens. So the 3 hydrogens aren't completely equally spaced out in 3D, and so that is going to create a polar molecule because the bond dipoles are not going to cancel because it's not completely symmetrical. So because we have a polar bond and not a symmetrical molecule, we also have a polar molecule. And so we are either going to have dipole-dipole or hydrogen bond. And here I have hydrogen, which could then be attracted to nitrogens from a neighboring atom. So if I have another ammonia here, So here we have hydrogen bonds because we have the hydrogen from one atom being attracted to nitrogen in another. Hydrochloric acid, so here we had 3.2 and 2.2, so we have a delta En of 1, so polar bond. It's not symmetrical, so it's also a polar molecule, and so we're either going to have hydrogen bond or dipole-dipole. Although we do have a hydrogen, it needs to bond to nitrogen, oxygen, or fluorine, which we don't have. So this is going to be dipole-dipole bonds. So water, here we have, so we've talked a lot about water already, so hopefully we know water is a polar substance, and because we have hydrogen and oxygen, that's going to create hydrogen bonds. So our delta En there was 1.2 between hydrogen and oxygen, and then because it wasn't symmetrical, there is not a canceling, so polar molecule. So we have that positive and negative, and then because we have hydrogen and oxygen, so the hydrogen from one water molecule can bond to the oxygen of another. So that is going to be hydrogen bonding. Next one here we have is ethane, and the difference between carbon and hydrogen is 0.4, which makes it nonpolar. And so because the bonds themselves are nonpolar, so we're going to have a delta En of 0 here, and then each of these is 0.4, which is nonpolar. That means the molecule overall is going to be nonpolar, and that means that we can only have the weakest, which are London dispersion forces. And the last one we have is nitrogen Tri Iodide. So there we have 3 for nitrogen, 2.7 for iodine. So each of the bonds between nitrogen and iodine has a delta En of 0.3, which makes it nonpolar. And anything that has nonpolar bonds is going to be a nonpolar molecule, and that means it's going to have the weakest forces in between neighboring molecules, which is going to be London dispersion forces.